and we'll start at the current slide. Okay. While that's coming up, let me go over a couple of just sort of minor things. Just found out I've got another office hour modification. Ashlyn's here. Okay. And that is, I found out tomorrow afternoon, normally I have office hours 3:15 to 5:15. Tomorrow afternoon I've got to leave right after my 3:15 class is over, because I got to go into Birmingham, pick up my wife, and head out to Jasper for something, and then we're coming right back. But we've got to do it before the business closes in Jasper. So it's going to be no office hours tomorrow afternoon after 3:15. I just told the student in my last class I'd meet her for advising then, so I've got to see her tomorrow and tell her. Thank you. Sure. All right. You all give me a little bit to grade on. Thank you so much. Okay. Okay. Any questions on anything we've done so far? All right, let's talk about what today's progress should be. We're on page 45 in chapter 2. This is a long chapter. We're going to finish Newton's third law, do a couple of examples, go into momentum and impulse, then forces and circular motion, do a few more problems, and Newton's law of gravitation, and then Earth satellites, weightlessness, and we'll be almost at the end of the chapter. Now, if we get all that done in the first 2.5 hours, or what's left of that 2.5 hours, then we'll go to lab. I think we'll be able to finish all this in that time. We'll go to lab, and this time the lab will be down in 259 if there's not a class in there. I think that we might be able to swing it, but there may be a class coming in there sometime or another, and if there is, then we're going to have to work around however we need to. Kedrick is here. Okay. So right now we're just missing Aaron, who we haven't seen from the beginning, Chelsea, Sean, and Scotty. We haven't seen Sean or Scotty since since the first week, so I don't know what's going on there. Okay. So if we can, we're going to go down to room 259. That's down the half flight of stairs. It's the first classroom on the left, but it's about midway down that hall. And there's a lab in there. We will be set up to do it there. I've got most of the lab set up. I didn't want to put it out in the countertops yet because I didn't know if there's a class coming in and some people would be messing with it. Okay. Any questions? Okay. If we indeed do finish the chapter today, which I think we will, we may even get started on chapter 3. We probably won't get too far into chapter 3, but somewhat. Then we'll do the last lab in chapter 2 today. And then if we get started in chapter 3 and say the first 2 hours next time, we get enough covered to do a lab in chapter 3, then we'll do that. And the test for chapter 2 will be the last 30 minutes on Thursday, if we finish the chapter today. And I think there's a good chance we will. All right? Any questions? Okay. We talked about Newton's first and second laws. Someone briefly fill me in on what's his first law. Not that briefly. Okay. A little more detail, okay? Newton's first law.
The law of inertia.
Okay, the law of inertia. And that means whatever a body is doing, okay, an object's doing, if it's moving, it tends to keep moving in a straight line, constant velocity, unless acted on by an unbalanced force. If it's at rest, it tends to stay at rest, unless acted on by an unbalanced force. Newton's second law then.
Forces causes acceleration.
Okay. If it is acted on by an unbalanced force, then it's given an acceleration. Forces cause accelerations. If something accelerating, it's got to have a net force acting on it. Okay? So now we're ready for Newton's third law. A little bit of differences between the first two and this one. The first two laws deal with talking about an object. Okay? An object. Whether it's at rest or it's moving or if it's accelerating, have net forces on it. It's always talking about an object. Okay? The third law of motion veers off a little bit here. The source of the force, okay, almost a rhyme every time, is some other object. Okay? The third law relates forces between two objects. Here's one rendition of it. Whenever two objects interact, the force exerted on one object is equal in size but opposite in direction to the force exerted on the other object. And remember, forces are what kind of quantity? Vector quantity. They have both magnitude and direction. So if there's two objects interact, okay, a transfer truck and a Volkswagen, okay, the forces exerted on each of them are equal, okay? Believe it or not, they are equal. It's just that and they're exerted on opposite directions of each other, okay? Tennis racket on tennis ball, whatever. Any two objects interact, force exerted on one object, equal in size, opposite in direction to the force on the other object. I don't know what this stupid message keeps coming up. Okay. Did everybody get the first slide? Okay. All right. Whoa. That's all they say about Newton's third law. Okay? There is an equation on page 45. F of A due to B is equal to F of B due to A. That's in magnitude. If you included directions, you have to have a minus sign in front of it. Okay? Now, let's get just a few small examples before we move on to, I'll do this back on Newton's second law. Okay. They have a couple of things here, illustrations here. One is a couple football players. Okay? Can't tell where they're from, but anyway, I recall back, I went to a very small high school in Georgia where just about anyone who wanted to could go out and play. Wasn't very good at it, but I remember when I was probably a freshman, we were scrimmaging, second team was scrimmaging against the first team, and Bill Boyce, the fullback, actually was our neighbor. We lived out in the farm out in the country, and he had the farm adjacent to ours, his father did. They were dairymen. And Bill, I think for most of his life, drank milk rather than water, okay? He was big, and he was strong, and he was, you know, it wasn't heaviness by fat, it was mostly muscle. He was the fullback. I was playing defensive end on the second string, and believe it or not, this time they were running some sort of a sweep my way, and the pulling guard came down, and amazingly, I got by him just in time to see Bill barreling full speed at me. And all I had time to do was wrap my arms around him, around his legs. Okay, about 5 yards down the field, with the knees pounding in my chest, finally we both went down. Okay? The force I exerted on Bill was equal to the force he exerted on me, Newton's third law. But, let's go back and just, wait, going wrong direction. Yeah, oops, still not. Goodness gracious. Oh, there it was. Okay. The forces were equal and opposite. I felt it a lot worse than he did, I guarantee. Why? He had more mass and more velocity. Okay? We'll get to that a little bit later. And I was sitting at rest, And all I could do was grab and hold on. Newton's third law. I'll bring that one up again a little bit later. I actually hit it a little too soon. But that's the one illustration of Newton's third law. Okay? We'll hit some others later because they go really well with the next topic, which is momentum. So let's go back and do example 212. Okay? All right. Now remember our spacecraft satellite out there, and we talked about, with no friction, no anything bothering it, it's just hanging around out there. Now we've got somebody bothering it. It's a 60 kilogram astronaut. What's 60 kilograms a measure of? Okay, mass, okay. Okay, height. Okay, so that's the mass of the astronaut. Okay? He's freely floating in space. He pushes on a freely floating 120 kilogram spacecraft. So this is also a mass, and this is the mass of the spacecraft, satellite, whatever you want to call it. Okay? And he pushes on that with a force of 30.0 newtons. That's the force of the astronaut on the spacecraft. Okay? Force of the astronaut on the spacecraft. And he pushes on it for 1.50 seconds. Second and a half. Okay? And that's the time interval. Okay? You can call it delta t or t. Okay? I'll prefer delta t, but the book usually doesn't use that. Okay? Now, the A part of this problem, okay, says compare the forces exerted on the astronaut and the spacecraft. We know that the astronaut pushes on the spacecraft with a force of 30 newtons. What does if any, does the spacecraft push on the astronaut? Newton's third law. Second?
I mean, whenever two objects interact, the force exerted on one object is equal in size and opposite in direction to the force exerted the other object?
Exactly. So the force on the astronaut would be 30 newtons as well, except in the opposite direction. If the astronaut pushes this way, the force on him is that way. Okay? If he's pushing this way, the force on him is that way. So that is very good. A is 30.0 newtons. This is the force of the spacecraft on the astronaut. And you could just put a minus sign there or just say opposite direction, whichever you prefer. Okay? Now B, compare the acceleration of the astronaut to the acceleration of the spacecraft. Okay? Now A was exactly 30 newtons. It's just in the opposite direction. Okay? Now, what was the acceleration of, the astronaut to the acceleration of the spacecraft? So the acceleration of the astronaut, that's one thing we're looking for. Acceleration of the spacecraft, that's the second thing we're looking for. How do we get those? Very good. Where does that come from? Second law. Newton's second law, exactly. So force on the astronaut is equal to the mass of the astronaut times the acceleration of the astronaut. Okay? Do we know the force on the astronaut? 30. So that's 30.0 and it's newtons, but what is a newton? Basic units. Say again?
Meters per second squared.
Okay, that's acceleration. And a force is a mass times acceleration. So that would be a kilogram meter per second squared. Okay? And that's equal to the mass of the astronaut. Mass of the astronaut? 60. 60.0 kilograms times acceleration of the astronaut. That's the thing we're looking for. It's a pretty ugly 60, isn't it? I erased too much. Okay. So what would be the acceleration of the astronaut? What would you do? Divide both sides by 60. What does that give us? 30 divided by 60. Not that hard. Say again? Okay, here.
30 divided by 60.
Yeah. It's what?
2.
60 divided by 30 is 2. 30 divided by 60 would be 0.500. We've got 3 significant digits everywhere, so it's 0.500. I just don't have enough room to write. And that would be, so the acceleration of the astronaut would be 0.500, and the kilograms would divide away, cancel out. And what units would you have left? Your meters per second squared, a great unit for acceleration. Okay? Now, it also says compared that to the acceleration of the spacecraft. Okay? Now, the other way to do this is just go on and divide. So if we had done that, divide with the letters, it'll take up less room if we do that. This acceleration of the spacecraft would be the force on the spacecraft divided by the mass of the spacecraft. And what would that be? Force on the spacecraft?
30 newtons.
Okay, and what's a newton? What's that unit? Fundamental units?
Kilogram per second.
Kilogram meters per second squared divided by, and what was the mass of the spacecraft? 120.0 kilograms. Notice the kilograms go out like they did before, and 30 divided by 120, that's the same as 3 divided by 12. Anyone know what that is? 0.250. So this would be 0.250, what units?
Meters per second.
Per second? Squared. Exactly. So, the forces are equal, but the accelerations are not, because the masses are not. Because the spacecraft is more massive, it accelerates at a slower rate. Because the astronaut is less massive, he accelerates at a greater rate. Okay? Now, the bad news is, out there in space, with nothing to stop him, if he's not tethered to something, he's accelerating like that forever. Okay? Just keeps on trucking. And he might miss his spacecraft after a while. Most of the time they tether themselves to something so they don't just drift off into space. That happens, okay? So we don't want that to happen. So 0.25 meters per second squared. Any questions on that? Can I erase it? Yay? All right. Let's get it erased. Let's do example 2.13. After the interaction and acceleration between the astronaut, I wish I'd have left it up there now, but I didn't have any room, and spacecraft described in example 2.12, they both move away from their original positions. what is the new speed for each? Okay? So, let me write down what we know. Okay, what do we need to know to calculate speed or velocity? What do we need to know to calculate velocity? Let's actually call it V final. What do we need to know?
Meters per second squared.
Okay, now that's a unit, but it's not even a unit of velocity. That's a unit of meters per second squared. What's that a unit of? Okay, meters per second squared. That's units. What's that unit? Units of? It's not a velocity unit. What is it? We just named it. Second?
Acceleration.
Acceleration. Meters per second squared is acceleration. For velocity, does anyone remember some of the formulas for velocity? Be helpful to write down for the test. V final specifically. Okay, VI, your initial velocity, plus AT. The initial velocity is how fast you're originally going, and the AT is how much the acceleration is increased or decreased that velocity, right? So that would give you your final velocity. Now, if they were initially, and I believe it said this, freely floating in space, and the spacecraft is also freely floating in space, so what does that mean? Initial velocity is 0. Okay, so initial velocity is 0 for both of them. Okay, so we'll have final for the astronaut. That would be acceleration of the astronaut. And the time was the same for both, remember? Okay, we'll also do V final for the spacecraft, and that's going to be, because it was also 0 initial velocity, acceleration of the spacecraft times that time over which the forces were acting. Now, what was the acceleration we got for the astronaut? Anyone remember? You wrote it down or not? 0.500. What units for acceleration? Meters per second squared. And what was the time interval? They told it to us. We hadn't used it yet. 1.50 seconds. 1.50 seconds. When you multiply those together, the second, one of the seconds goes out over here, and that gives you 0.5 times 1.5, and I'm pretty sure that is 0.750. What units are left? What units are left? Second? Meters per second, which is a great unit for a velocity. So your final velocity of the astronaut will be 0.75 meters per second. How about for the spacecraft? What was its acceleration? We just calculated it. Anyone remember what it was? 250. What units? Say again? Meters per second squared. Multiply that by that same time interval, 1.50 seconds. And what does that give you? I think it's about 0.375. Have you got it? Is that right? I'm doing it in my head. I may have missed it. Yeah. 375 what units? Meters per second, because the second cancels out. And that's the final velocity of the spacecraft. So again, the more massive spacecraft has a slower acceleration, also a slower velocity, final velocity. The lighter weight astronaut, less massive astronaut, has a larger acceleration and therefore a larger final velocity. Again, if he's not tethered, He's going to keep on trucking at that ad infinitum. Okay, hope he'll run into another spacecraft sometime or another. Probably won't. Okay, so they got 0.75 for the astronaut meters per second, and for the spacecraft 0.375 meters per second. Very good. All right. The other example of Newton's third law, this is probably a little more appropriate than the other one I was going to say. Any of you ever been fishing in a lightweight bass boat, aluminum bass boat? Okay? Right. And have you ever been pulled over to the side and your buddy was supposed to have tied it up? Now just imagine this, but didn't. And you go to step off, and what happens? It goes out because you're exerting a force on the boat's exerting a force on you. It probably is lighter than you are. That's why I said lightweight aluminum. And it goes with a greater velocity. You go with a fairly small velocity and could possibly go right into the drink. And you no longer have a buddy because something terrible happened to him. Okay. All right. But I was also in the Navy on an aircraft carrier, also on an ammunition ship. I can remember several times stepping onto that, or stepping off of that to go ashore, and I didn't notice it moving at all. Why?
A lot heavier.
Say again?
A lot more mass.
A lot more mass, okay? So in the previous thing, the bass boat was much less massive than the person, so therefore it goes at a greater velocity. You go to a small velocity, except downward, okay? And the aircraft carrier, huge mass, doesn't even notice it. And you pushed off. That little bit of force means nothing to its acceleration or velocity, and it just sits there, okay? It was tied up, though, but that wasn't the reason. Okay, so that's Newton's third law. Any time you exert a force, now I've heard that Newton said it this way: if I push on a rock, this isn't a rock, but let's say it is, the rock also pushes on me, and you can see the indentation in my finger that I push on the desk, and the desk pushes back on me. Forces are equal and opposite, okay? Now, it's a very good jumping point then to go to the next concept. Any questions about Newton's third law? Okay? This is the concept of momentum. And the lab today is in two parts. The first part we're going to deal with Newton's laws. The second part will deal with momentum. That's why I'm hoping we'll finish this today so we can accomplish the lab today. Well, momentum, an important property, closely related, it says, to his second law. It is, but I feel like it's even more closely related to the third law. Okay? To all of them, in fact. Now, remember I said Newton wrote this famous paper. The name is Principia, is what people usually call it. It had a big long title. That was the first word. It means principles. But Principia is an English word. He was British, English. Okay? Where did that come from? Well, back in his day, all scientific writing was done in Latin, a language no one used except the church and science, okay? They're the only people that used Latin, but he wrote because it was required to write in Latin, and supposedly all scholars knew Latin, so therefore they could read it even if they were French or Russian or English or Yugoslavian or whatever, you know. They could always, they didn't have Yugoslavia back then, but anyway, they would be able to read the scientific literature. Well, I've not read it, certainly not in Latin. I don't know Latin, but the way I understood it is Newton never referred to mass, well, he probably sometimes did, or to velocity, or to forces that much. What he referred to was his quantity of motion. And what he called a quantity of motion was exactly this. The mass of the object times its velocity, that's what he considers the quantity of motion. Mass times velocity. That's what we call linear momentum. The symbol is P. Where they got the P, I have no idea. Maybe that was the Latin word that he used that meant quantity of motion. I don't know. Maybe that's where P comes from. I have no clue. Okay? Now, it includes both the motion, velocity, and the inertia. Inertia is related to mass. Now, if you go back to Newton's first law, remember we used to say a quantity, an entity at rest stays at rest unless acted on by an unbalanced force, or in motion stays in motion, straight line velocity, constant velocity, unless acted on by an unbalanced force. Here's how you say it, referring to Newton's quantity of motion. An object's quantity of motion does not change unless it's acted on by an unbalanced force. See, that includes zero velocity or any velocity. Okay? The quantity of motion does not change. Okay? Second law, the time rate of change of the quantity of motion is the measure of the force. That's exactly what is much shorter than, well, F equal ma is not too long, but everything in terms of this quantity of motion, momentum, and all the laws make perfect sense. They tie together so nicely. Okay? Here is the astronaut pushing on the spacecraft again. Exactly the same problem we just did. 60 kilogram astronaut, 120 kilogram spacecraft. Boy, that must be pretty dense because it looks smaller than he does, or she does, or whoever it is. Velocity was, remember we calculated 0.75 meters per second in this direction. Spacecraft velocity 0.375 in that direction. Momentum here was 60 times that. Let's see, 3/4 times 60. That would be 45 kilogram meter per second in this direction. Multiply that. I think it's 3/8 times 120. I'm pretty sure that is, someone types that in for me, make sure, but that would be 45 kilogram meter per second in the opposite direction. 127.375. Okay. All right. Yeah, there it is. 45 kilogram meter per second this way, 45 kilogram meters per second that way. Why was that true? Because initially they were both at rest. Same force exerted, equal and opposite, equal momentum, not equal velocities, not equal masses, not equal accelerations, but equal momentum. Okay? In the opposite directions. Okay? And in this case, the forces happen to be equal too. You will find that so true in momentum. In fact, that's one of the key elements of physics. There are several of these, what they call them, invariants, things that do not change. One is mass, okay, except the nuclear reaction, but we won't go there, okay. Mass is typically invariant. The mass of an object does not change no matter what you're doing to it, okay. Weight can change, right? Depends on your gravitational field, okay? Mass does not change, it's an invariant, okay? Momentum's another one that does not change. Next chapter we'll talk about total energy, does not change. We call these the conservation principles. So the conservation momentum is the total momentum of a group of interacting objects remains the same in the absence of external forces. The total momentum of the system remains the same. Okay? Now, I'm guessing a few of you have fired a rifle before, right? Okay? Now, initially the system is at rest. Momentum of the system is 0. No velocity, no. When you pull the trigger, the bullet takes off at a very high velocity. Okay? Fairly small mass, but very high velocity, so now has momentum in that direction. How about the rifle? Right into your shoulder. So holding that rifle off your shoulder, not a good idea, okay? Because you then dislocate your shoulder, okay? Or bruise it really, really, really badly. So what do? You snug it up just as tightly as you can against your shoulder, and now you become part of the system too. You've added a lot more mass to that problem, so now you do have a change of momentum, but it's very small compared to what it was otherwise. Yes?
Wouldn't the gun still push on your shoulder if you were punched like that?
Yeah, it's still, yeah, you still feel it, but you don't have it doesn't have a significant velocity, and you are part of the system now. You're so much more massive, you and the gun, that you have a much smaller acceleration and a much smaller velocity. But you do move backward, okay? If you've ever seen, they had a bunch of these in Vietnam. We had several of our older battleships out there shooting the 16-inch triple-barreled guns toward the coast of Vietnam, and you see the entire ship, huge battleship, move in the water in one direction. I mean, the conservation momentum. Okay? Now, so believe it or not, the total momentum of the rifle in this direction is equal to, but opposite to, the total momentum of the bullet in that direction. That's why I say this is far more closely related to the third law, Newton's third law, to me than the second. It's related to all of them, but this is classic third law activity. Momentum, just like equal opposite forces. Now, we're going to do some problems with that in a minute. Collisions. I hope that you've never been in a collision on the highway. No, okay. But I remember my first, I went to Georgia Tech, and my older brother had been there 2 years before me. And he had some friends, there that he had made over the previous 2 years. And one of them had a vehicle, okay? We didn't have a vehicle at the time. This was a different age from what you guys are used to, okay? And Frank Michelle had a nice little, I think it was a Z28, but nice little car. Kept it real thing. Drove it like crazy, but and we were going to see Easy Rider. I don't know if y'all remember that. Classic movie, okay? It was freshly out at the time. And we were going to see Easy Rider. They were playing at the Capri Theater in Atlanta. And Frank didn't know exactly where that was. And my older brother was sitting in the front seat with him. And he was sort of directing him, because Mike kind of knew where it was. I was in the back seat. Z28s don't have much back seat, but I was right in front of the rear tire, okay? And we were going along. Frank was driving probably a little too fast, but anyway, Mike was watching it. There it is, okay? So Frank turned. When Mike said, there it is, he turned. And here came another car that hit just after where I was sitting, okay, on the rear right fender, okay? My first week at college, I was just in a car accident, okay? And of course the other guy had slammed on brakes when he saw Frank turn in front of him, and he skidded up until he arrived at the car. Not enough time to stop, as we helped him stop. Well, what did the officer do when he came? He got up there and measured the skid marks. Now, they couldn't tell him much because he didn't go to a full stop, but what he was doing was measuring the best he could the change of momentum of the car, to estimate speeds, okay? Because you can get that from here because the momentums are equal. So collisions, they just about always do it. They're out there with the tape. I don't know if you've ever seen them measuring the change of position, change of momentum of the object. Also analyzing reactions, interactions again. boy, they got a lot of actions in there, didn't they? Okay, and that's, to me, classic third law. Okay. All right. Before we move to impulse, let's do a couple of examples with momentum. And I'm going to have to find, that's probably our best slide to do them on. We don't have a lot of room, but let's do it. Example 214, page 48. A 20,000 kilogram railroad car, okay? 20,000 kilograms, okay? That's supposed to be a nice level track here, okay? What's that a measure of? Mass, okay? So this is, we'll call this car 1, okay? And the mass of car 1 is equal to 20,000 kilograms, okay? Is coasting at a speed of 3 meters per second. What's that a measure of? Okay, speed also, you could call it, with a direction on it, velocity. Okay, there's your velocity. Okay, when it collides with, okay, here's the things on it. When it collides with another, and this is supposed to be identical, I don't have enough room to draw it. Okay, an identical freight car, and when it says identical car at rest, okay, identical meaning exactly the same mass. So the mass of car 2 is also 20,000 kilograms. Okay, but this one's at rest. What does that tell you here?
0.
Say again?
0. It's 0.
What is 0?
The mass.
Not mass. Mass is 20,000. Velocity. The initial velocity of car 2 is 0. This is the initial velocity of car 1. Okay? Now, it collides and couples with, meaning it doesn't bounce off, but it couples with. That's why I drew the little couplings here. And when it collides, they automatically attach themselves, so one doesn't bounce one way and one the other. They stick together. Okay? Now, how you deal with a situation like this is you calculate the momentum of car 1, momentum of car 2 initially, and then after they couple, guess what the momentum is? The same, because it's conserved. So then you can calculate the speed of the coupled cars. Okay? So what was the initial momentum of car 1? What is the formula for it? What is momentum? It's right there. Mass times velocity. There it is, right there. I said it was a convenient thing to have here. So it's mass of car 1 times the initial velocity of car 1. And what would that be? Mass is 20,000 kilograms. And what's the initial velocity of car 1? 3 meters per second. So its initial momentum is 60,000. Now here's the sad news. There's no unit for momentum. Okay? So we have to write kilogram meter per second. Now it just seemed weird to me, since this was Newton's quantity of motion. Seemed like to me this is what we ought to call a Newton. Let force be whatever else you want to call it. But they named Newton forces after Newton. They didn't name momentum after him, which I thought would have been more appropriate. But who am I? Okay? Nobody. Okay. So, what was the initial momentum of car 2? Second? Okay, its mass is 20,000. But what's its initial velocity? 0. And 20,000 times 0 is? 0. So the initial momentum of car 2 was 0. So what's the initial momentum of the system of the two cars? 60,000 kilogram meter per second. Now, after they collide and they couple, okay, what do you think the final momentum of the system is? 60,000, because momentum is conserved. You don't lose it, okay? So it's 60,000 kilogram meter per second. But now, with the coupled cars here, what is their mass? 40,000, because they're each 20,000. So the 60,000, this is the initial momentum, but it's also the final momentum of the system, and this is equal to the mass of the system, which happens to be 40,000 kilograms, times the V final for the whole system. Okay? So what we do, if we're looking for final velocity, and that's what it is, what is the resulting speed of the combined cars, then you divide both sides by 40,000 kilograms. Divide this by 40,000 kilograms. And notice the kilograms go out, and bunches of these zeros go out. And what's 6 divided by 4? 1.5. 1.5. We'll just leave it 1.5. What units? Meters per second. That's the final speed of the combined cars. Okay? Now, sadly enough, they chose this as the time to round that to 2. That's ridiculous. Leave it 1.5, okay? Sure, they only gave that to one significant digit there, but my goodness, it's not 2, it's 1.5, okay? So, otherwise the problem hardly makes any sense, okay? Now, any questions on that? Okay? If you thought my rail cars were ugly, just don't say it. Let's do example 2.15. A student and her rowboat have a combined mass of 100 kilograms. So here she is on the water, okay, in her little rowboat. Okay, here's the paddle going out into the water. Okay, pretty ugly paddle. And here she sits in her little rowboat, okay, and, you know, she's got hair, okay. There she is in her little rowboat, okay? And their combined mass, the mass of the system here, is 100.0 kilograms, okay? The trouble is she lost her paddle, okay? So she stands in the motionless boat. What does that tell you? Motionless boat. What is? Initial velocity is 0. Very good. Standing in the motionless boat in calm water, she tosses a 5-kilogram rock. So she stands up now. Okay. Okay. She stands up and tosses a rock. Okay. In this direction, a 5.0 kilogram rock. What's that a measure of? Mass of the rock. Okay? The mass of the rock. She tosses that out of the back of the boat with a velocity of 5. Velocity of the rock is 5.0 meters per second. Okay? What will be the resulting speed of the boat? Okay? Again, you use conservation of momentum. The system originally had 0 momentum. 0 momentum. Nothing. Okay? When she throws the rock out the back, what is the momentum of the rock? I'm sorry. Momentum of the rock. P for the rock is mass of the rock times velocity of the rock. And what would that be? No. 5 times 5. 25. You can put 0, you don't need to. Kilogram meter per second. Mass in kilogram, velocity in meters per second. The rock's going that way. Originally, the system was at rest. The rock's going that way with a momentum of 25 kilogram meters per second. The boat has to go that way with a final momentum of 25 meters per second. Well, so the momentum of the boat must be in the opposite direction, also 25 kilogram meter per second, just in the opposite direction. Well, what is the momentum of the boat then? Mass of the boat times velocity of the boat. What was the mass of the boat? Say again? 100. So this is 100.0 kilograms. So divide both sides by 100, and what do you have? Again, the kilograms go out. 25 divided by 100 is? Move the decimal 2 places. Say again? 0.25. Okay? So velocity of the boat is 0.25 meters per second. Not going very fast, but is going to the shore. So if she threw the rock away from the shore, that's going to push the boat toward the shore. Will it get there? Eventually. If there was no friction, but even water has friction. So if she was close enough, that could enter there pretty slowly. How many more rocks you got in there? Okay. Now, to me, there's a little something wrong with this problem. If the total was 100 here, and she threw 5 out, then now the system is not 95 kilograms. But they're not taking that into account. They didn't count the rock as part of the system before. But that's what they get, 0.25 meters per second. Pretty slow, but at least it's heading to shore now. Any questions on momentum? Very, very short and quick on both Newton's third law and momentum. All right. The next concept is kind of going to tie them together. Okay? And this is the concept of impulse. All right. Here's one definition of an impulse. A force acting on an object for some time interval. We basically did this in that previous problem, or came close to it anyway, where the guy was pushing on the spacecraft for 1.50 seconds. Okay? That was a force acting for some time, t. Okay? The force was in newtons, and the time usually in seconds. Okay? Now here's another feature of an impulse. An impulse produces a change of momentum. If you push on an object, okay, this object's at rest. I don't know what its mass is. It's not very massive, but it's got that thing. I push on that over a certain time, and I give it a velocity. Now, friction is going to make it slow down and stop, but I produced a change of momentum. Had 0 momentum when I pushed on it. It had whatever its mass was times its velocity. I produced a change of momentum. I provided an impulse to this. Okay? Now, I'm going on to the next slide before we come back to the applications. Okay? Now, as I said before, momentum is mass times velocity, right? That was what Newton called his quantity of motion. Okay? And what did we do with most things? When we first came up with distance or displacement, one of the next things we did was take the time rate of change of that distance or displacement, and that gave us a speed or velocity. Change of distance over time is speed. Change of displacement over time is velocity. And then once we had a velocity, divide by time again. You did it in lab. And what did you get?
Distance. No.
Meters per second divided by second. You did it in the second lab. Okay, you measured the distance on the ramp, remember? As you went there. And the change of distance over change of time. Distance divided by time was?
Acceleration. No.
Okay, that's the answer to my previous question. Distance divided by time is velocity. Velocity divided by time is acceleration. So you see, every time almost we come up with a new quantity. Well, let's take the time rate of change of it. Well, guess what? We came up with momentum. Let's take the time rate of change of momentum. Well, guess what that is? Let's actually do it here. Momentum is mass times velocity, right? And when you do a change of momentum per unit time, okay, well, guess what? The mass doesn't change any. It's invariant. Mass doesn't change. So you can call this as m times delta v over t, right? Because mass doesn't change. It's the velocity that changes. What is change of velocity over time? Say again? Change of velocity over time. I just asked the question a few minutes ago, and John answered this question in the wrong spot.
Slow reaction time.
Say again?
I said that was slow reaction time.
Yeah. What is the change of velocity over time? You did it in lab. The second lab. Acceleration, exactly. And what's the mass times the acceleration? Yeah. Something equals ma. Someone gave it to me earlier. Force! That's it! So you see the force is change of momentum over change of time, or the time rate of change of Newton's quantity of motion. That is how he defined force. We call it mass times acceleration because change of velocity over change of time is acceleration. But he called it the time rate of change of this quantity of motion. So that's P final minus P initial over T. Now, if you're dealing with stopping, the final momentum is zero. If you're dealing with taking off from rest, the initial momentum is zero. So this can be used with when one of these is zero or when neither is zero, okay? So that is your time rate of change of momentum, is the force. Now, how do we get impulse out of that? Force acting for some time. Multiply the delta t, or the t, by the force, and that gives you impulse. The t's go out here, so your impulse is equal to force times the time interval. I like to call that delta t because it's usually an interval, okay? Now, that's also a change of momentum, okay? Now, let's go back to some of those examples. I can remember as old Mr. Goodness, I can't think of his first name now. A friend of ours that went to the same church, he was an older man, but he used to say, back when I was a boy child, back when I was a boy child, the cars that we had nice metal dashboards, okay? And you know what you called the passenger seat at that time? The death seat. Because if you were ever in an accident, you're going right into that, either the dashboard or the windshield, both of them awfully hard, okay? And why was that true? Because if you're in an accident, you're tooling along at 60, 70 miles an hour, lose control, hit a tree, you're going to come to a stop. That's a pretty big change of momentum. The mass of the car, pretty massive, at a pretty high velocity, and coming to a stop, that's a huge change of momentum. And if that change of momentum took just a very small time, then this force is huge. Because the change of momentum is huge, divide that by a very small time, that makes it even bigger. That force is enormous. And if that's just a metal dashboard there, the time it takes your face to stop against that metal dashboard, or your chest, or any other part, is going to be incrementally small, and therefore the force is going to be incredibly large. And that's why people died in the passenger seat. Now, the driver didn't suffer quite as badly because he had the steering column that would collapse under him, so it would take a little bit longer. So usually his injuries lingered a bit longer because they weren't quite as serious. But that passenger in miserable shape. Now I can remember a car, it seemed like it was a Plymouth. I can't remember what the make was, what model of Plymouth it was, but the first one I saw that had padded dash. Still had a metal dashboard, but it had maybe an inch of padding on it. Now that doesn't sound like much, but then if you hit that dashboard, you had to compress the pad before you got to the metal. And that took maybe a second or a fraction of a second. But anyway, the time interval went from almost instantaneously to instantaneously plus a fraction. So any kind of increase you had here, because the impulse was the same, the change of momentum was the same, but now the force was much less. And that's why football players wear all the pads they do. That's why their helmets have all that strapping and cushioning in them, trying to increase the time interval over which their head stops, as opposed to in the old days. This is long before my time, folks. They wore leather. Yeah, and they died. You know, oh no, they suffered pretty bad. Okay, or they just didn't hit as hard. Okay, or whatever. And the players were lighter weight, meaning less mass, and probably weren't as fast either. Today, I'm not sure the helmet technology is keeping up with the increase in size and speed of the players doing the hitting, okay? But the greater the time. So I remember the padded dash, a great improvement. You might not die instantly, it might just damage you pretty badly and lingering. No, okay. Well, after that, another requirement came in. Seat belts. Now, rather than you hitting the dash immediately when the car stops, you're held back by the car, so you try to go forward, but the seat belt holds you back, so that change of momentum takes several seconds, 1.5 seconds, or something like that. But you greatly increase the time interval for change of momentum, and now the force is even less. Okay? And then after the seat belt, they came out with the shoulder strap too. Originally it was just seat belt, then the shoulder strap, and that took even longer for you to reach it. You could still reach the metal dashboard, and by this time they probably were making them out of better material, but the time interval was even longer, so the force was even less. And nowadays, airbags. They deploy when they sense that change of momentum, and they blow up, and now it takes you, it doesn't seem like long, but it does take you much longer before you, in fact, you may never even touch the dashboard. Hopefully you won't, if the airbag does its job. So the time interval is much greater, the force is much less. Okay? Examples of change of momentum, impulse, force times the time interval. Change of momentum never changes. You still hit the tree, change from 70 to to zero in a very short period of time, but the time it took you to impact the status was much greater, so the force was much less. Were y'all born in 96? Okay. No? No. Okay, 2 years off. In 96, the Summer Olympics were in Atlanta, Georgia. Okay? And we went over and saw a few tennis matches, I think it was, but that's about all. But I remember seeing on or hearing the report of it. Fortunately, it didn't show this on television. There was a little Chinese gymnast, female gymnast, and they do something called the vault, where they run as fast as they possibly can down this long stretch of gym floor and hit this springboard and fly up into the air, doing as many somersaults and twists and spins as they can, bounce off of a pommel horse and still doing twists and spins, and then try to land and stick their landing. Well, this poor little gymnast didn't quite make a full revolution or overspun or something. Oh, and by the way, have you ever noticed the gym and track and field too, when they're having this, what do they have all over the floors? Pads and pads and pads. Okay? And the reason for that is to increase the time interval over which that change of momentum happens, so the forces are much less. Well, all these places were very well padded, except over here, and she got off track. She hit the gym floor. There, the time interval was almost instantaneous. The force was enormous, and she, I believe, was a paraplegic or quadriplegic after that. It completely broke a lot of her back, her spine. True story. I mean, sad story. If you've ever noticed the pole vaulters, the layers of pads that they land in. The high jumpers, I mean, they jump from the ground, but they don't land very far because it's just loads and loads of pads. Even the floor exercises, are you seeing how the floor gives on that? All sorts of things there. The high bars, all those things, they have lots of padding there. So the time interval increases, so the force when they land is not nearly as much. Okay? Let's go back to those old cars. What were the typical bumpers on those old cars? Chrome. Yeah, steel, metal, solid. Okay? Not a good idea, because guess what? They collide, instantaneous. Force enormous, because the time interval is very small. Today's bumpers are plastic, and don't some of them also have cylinders behind them, so you actually compress them, and then they...
Some of your older cars did too.
What's that?
Some of your older cars did too. Had the cylinder behind them.
Yeah, okay.
Even with the metal bump on there.
Right. Depends on how old you're talking about. I'm talking about the 60s. Okay. Did they have them back then? Really? Okay. I think
It's not as improved as it is now, but
right.
They have.
I think those were the high-end cars. My dad always saw. Okay. Okay. But yeah, anything you can do. In fact, I was at a math meeting a few years ago over in at Shelton State, and they brought in an engineer from the Mercedes plant to talk with us, and he said in the old days, they protected the engine well, okay, because the engine and that compartment was solid. Of course, that left the canopy, I mean the what do you call it?
The margin?
What?
You're talking about
Where the people sit. Don't they have a name for that? The cabin. The cabin wasn't that strong, so when you had an accident, nothing happened to the engine, and back here, the bumpers, everything were solid as they could be. It's the cabin that crushed. And of course, people got accordion. Okay. Nowadays, the way he was telling it, at least Mercedes, they put great strength in the cabin and allow a lot of flexibility as much as they can for the other parts to be the accordion. And much safer design. Why in the world we had that not at the beginning, I don't know. But in the old days, I can remember when the highway railings and things like that were concrete and solid steel and things like this. Nowadays, they use the wires now on a lot of the highways so that they give when there's an accident. So you don't have the car taking all the change of momentum. The barrier does too. And that's why when they're doing road construction, those plastic barrels are there to absorb and take some of the impulse away. Increase the time interval so it decreases the force during the, if someone were to collide with it. All right, so that's impulse. Beat that to death? Okay. Let's see, yeah, we already did that. Okay. Let's move on to forces and circular motion. This is 2.8 in your text on page 49, forces and circular motion. If you're traveling at a constant speed around the curve, net force 0? Why? Why not?
Would you have a constant force?
Okay, you have to have a force anytime you have a change of velocity. And remember, velocity is what kind of quantity?
Speed over time.
Yeah, but what kind of quantity is velocity? A vector quantity. And anytime you change direction, you have to have, that's a change of velocity. You are going here, you're going there. Even though the speed doesn't change, you change your velocity because you change its direction. Okay? And if you change the velocity, that requires, what's the change of velocity over time? You've answered this question several times. Or I've wanted you to several times a day. Change of velocity over change of time?
Force.
Acceleration.
Acceleration.
Oh.
And acceleration, if you have an acceleration, what must you have? What produces an acceleration? A force, exactly. So, if you have circular motion, there has to be a force involved. Okay? Because circular motion is accelerated motion. Not because you're changing speed, but because you're changing direction. And that acceleration is called an centripetal acceleration. Now, what word do you almost see in the first part of centripetal? Center. And that means center seeking. The acceleration is toward the center of the curve. Okay? The centripetal force is the force that must be making that centripetal acceleration toward the center of the curve. Okay? People talk about a centrifugal force, which is not really a force at all. It's an apparent outward tug as the direction changes, but it's not really. Remember that thing that you feel like you're being thrown out? That's because the car is cutting in front of you, forcing you inward. You feel like you're being thrown out, but it really isn't. So that's sort of a fictitious force. The centrifugal force, if you were to end it, then you get straight line motion, okay? I'm thinking now, you ladies probably didn't do anything dumb like this, but tie a rock on a string and swing it around your head. Oh, that was just, something was just fun about that, wasn't it? Some of you guys have done it, I bet, okay? But what if either the string broke or it slipped out of your hand? What you're doing when you're doing this, you get circular motion. The rock goes around and around and around, yes?
The question is, why would anybody want to do that?
You're alive.
Later I'm going to ask another question. We're a few chapters from now, I'll ask another one. And the vast majority of the guys in there will say, oh yeah! And you'll say, why would anyone want to do that? Okay? It's a gender malfunction or something. I don't know. Okay. Okay. Oh, okay. But in doing that, you're exerting a force. The string is pulling the rock always toward the center. And if the string breaks or it slips out of your hand, then it goes to straight line motion. And always there seems to be a window in that line. You know, it just about always happens, you know. That happens. Okay. So, if something is going around the curve, its velocity is in that direction, but the force is in this direction because, say, the velocity is here, the next instance is here, and if you drew the vector addition to that, that would point towards the center of the circle every time. Okay? So everything points toward the center. So your centrifugal force, your centrifugal acceleration is that way, generally perpendicular to the instantaneous velocity. Okay. And if whatever is pulling you in suddenly isn't pulling you in, then you continue straight line motion, as by Newton's first law, inertia. Toward a window, unfortunately. Okay. Now, the sad thing here is there's a couple of formulas you need to know. They didn't put them in the slide. Okay? So let's go back and we'll put them in. The centrifugal acceleration that they're talking about here, right here, is defined to be v squared, velocity squared, divided by the radius. Okay? Now, if you remember, and that is a 2 up there, pen drags and it makes it look like a 3. Velocity squared divided by radius. Remember I said earlier that most of the times when we have our variable squared, you're going to have a 1/2 in front. This is the one exception. I told you it was coming up where that's not the case. You do not have a 1 in front, a half in front of that. Most of the other things are at 1/2. You know, the distance is 1/2 at squared. Remember we had that acceleration times time squared. You have a 1/2 in front. This square doesn't have a 1/2 in front. Okay. Well, what would be your centripetal force? What is a force? Newton's second law. Y'all given it to me before today.
Change of momentum.
Okay, it certainly is, but our usual thing is mass times acceleration. Okay? Well, if it's mass times centrifugal acceleration, then this would be your mass times the velocity squared over your radius. Okay? So those are the two formulas you need here for centrifugal force, acceleration and centrifugal force. Equations 210 and 211. Examples 216 and 17 will use those. So let me clear this off the slide so we can do those examples. A 0.25 kilogram ball, what is that a measure of? That's the mass of the ball. Okay? Attached to the end of a 0.5 meter string, what's that a measure of? That's your radius, because if you're swinging it around, which we would, but yeah, that's the radius, because that's how long the string is. Okay? Moved in a horizontal circle at a speed of 2 meters per second. 2.0 meters per second. What's that a measure of? Velocity. Very good. What is the net force needed to keep the ball on a circular path? So we're looking for net force. And what will that force need to be? A centripetal force. So what would that need to be? Mass times velocity squared over the radius. What was the mass? 0.25 kilograms. Don't forget units. What's your velocity? 2.0 meters per second. But you're squaring that. Divide that by your radius. And what was your radius? 0.5 meters. Okay? So let's do the math. Okay, first let's square. Always remember your little acrostic. Please excuse my dear Aunt Sally. I don't know what she did, but please excuse her. Always do the exponents before you do your multiplication division. Yes.
Actually, I heard it that way, or parachute expert, my dear Aunt Sally.
Oh, really?
Yeah.
Okay, yeah, so you don't have to. Okay. I've also heard Aunt Sue, but whoever, whatever. It's always what's in parentheses, exponents, multiplication, division, whichever comes first, addition, subtraction, whichever comes first. Here we have exponents and multiplication and division, so we do this. So this will be 0.25 kilogram times what? 4.0. Second? You square your units too. Meters squared per second squared. And divide that by 0.5 meters. Okay? All right. Well, this meter will cancel one of those meters out. And that gives you, what is a quarter of 4? 345. No, I'm just kidding. What? Okay, 1 divided by 0.5 is? Anyone know that one? 1 divided by 1/2? 2, exactly. So this would be a force of 2, and we'll call it, let me see how many units they have. I think they only have 1. 2 kilogram meters per second squared. What's a kilogram meter per second squared? It's Newton, exactly, and that's a good measure for force. So you see, your units are helpful. They make sure that you get the things right, and that's exactly what they got, 2 newtons. So 2 kilogram meter per second is the same as 2 newtons. All right. Now, I wish I had more room to write, okay? What we're going to do here, example 2.17, suppose you make the string in example 2.16 half as long. So now the radius is not 0.5, but 0.25, okay? So that will be 0.25 meters, okay? That's the new radius. Half as long, 0.25 meters. What force is now needed? Well, now you divide by 0.25. Well, your numerator stayed the same as 1, but now you're dividing it by 1/4. So what's the new force? Say again?
Well, you're dividing.
Yeah, dividing by...
You're dividing 1 by 0.5.
By 0.25. You did divide it by 0.5, now it's by 0.25. Well, actually, the easy way to do it, this 0.25 cancels that 0.25, and that just leaves you 4. Exactly. Now your force is 4 newtons. So by having the length of the string, you double the force that is required. Okay? To keep the same velocity and everything else. Okay. All right. And that's what they should have. Yeah. And here they say 4.0 newtons. That is getting so picky because now everything has 2 significant digits when you go to 0.25 meters. So now they can say 4.0 newtons. They're getting a little crazy with significant digits, but it's fine. Okay. I've seen several people have to get up and break. Do we need to take a break now? Okay. So before we go to Newton's law of gravitation, which is the next topic, let's pause and all right, any questions on anything so far? I was waiting for the projector to come back on. Any questions? Boy, did Newton ever do a lot. One man, Isaac Newton, basically revolutionized physics, came up with the three laws of motion. He came up with the universal law of gravitation. He did far more work in optics than anyone had ever done up to his point. He discovered that light was made up of multicolors, like a rainbow. He came up to describe planetary motion. He had to develop a whole new branch of mathematics, calculus. Incredible what he did in a lifetime, okay? More than any other person I can even think of doing in a lifetime. Isaac Newton was there. Wow. So here's his law, his law of gravitation. Two objects, any two objects, all masses, okay? There is an attractive force between them, okay? That is the force due to gravity, okay? It's an attractive force. It's proportional to the product of the masses. So the bigger the objects, the bigger the forces, okay? Because I like this chair, but I don't see a lot of attraction between me and the chair. I'm not drawing it to me because it's fairly low mass. I'm relatively low mass. No way it's going to move toward me. Now, planets, stars, suns, moons, yeah, those are big enough masses, you'll see that, okay? Proportional to the product of the masses. Inversely proportional to the separation distance squared. Not just the separation distance, but the distance squared. So the further I am, the less attraction there is, okay? By a long shot. Now, it says here, this explains why G is equal to 9.8 meters per second squared. They don't say how it explains that, they just say it does. Our coming up example will go over that and see that. And this also provides the centrifugal force and acceleration for orbital motion. Why do we move around the sun? Okay? Second? Because the sun's gravity is pulling us in. But we have a velocity perpendicular to that, so that keeps us moving, just like swinging the string on the rock on the string. It keeps us moving in place. The gravitational force is like the string, and we're like the rock, and the sun's like us, the earth is like the rock. Okay, so let's use the Earth and Moon, okay? Earth is a fairly massive planet, very small compared to the larger ones, but a fairly massive planet. The Moon, amazingly, is one of the more massive moons in our solar system, even though we're one of the smaller planets. But the gravitational pull of Earth to Moon keeps the Moon on this path around us. It's always falling to us, but it has enough velocity this way that it keeps it from crashing into the Earth. Okay? Now, satellites we put out there, as in your GPS satellites, your communications satellites, your TV satellites, all those things, those satellites basically have to stay just about in the same place. So every now and then they have to boost them maybe a little bit to keep them from falling in, but they want them to stay exactly in the same position. The Moon is going around us. It's not staying over the same part of the Earth like a communications satellite would probably do. Okay? But that's why and Newton came up with this concept, universal law of gravity. Okay? And again, these slides are really fairly poor that they're not putting any of the formulas on here. Let me just look ahead and see if there are. Nope. Okay. No formulas at all. So let me put it on here for you. Okay? The force due to gravity, F, force due to gravity, this is Newton's formula he came up with. He said it was directly proportional to the product of the masses, mass 1 times mass 2, inversely proportional to the square of the distance between them, okay? And the proportionality constant, I put R, they put D, okay? It doesn't really matter. The proportionality constant is this number he called G, capital G. Now that's not the little g that we have there. It's capital G, okay? Now, if you think about it, what unit would G have to have? Well, this on this side is in newtons. This is kilograms times kilograms. That's kilograms squared. And this is a distance in meters squared. So this would be a Newton meter squared per kilogram squared. That's the unit for the gravitational constant. Okay? Universal gravitational constant. It's not just for Earth and Moon, not just for Sun and universal. Throughout the universe, this constant is fixed. Okay? It was first measured experimentally by Henry Cavendish in 1798. The accepted value today, this G is 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. That's what I told you the units had to be. Indeed, that's what it is. Now, so gravitational attraction. Now here's why the desk and I are not really all that attracted to each other. Look how small this number is. That's 0.000000000667. That's how small that number is. So no, any kind of masses that are fairly small, it's not going to notice any force like that. But when you get masses the size of a planet, the moon, the sun, a star, black hole and stuff, yeah, they really come into play there. But most small masses, anything we would deal with, not going to sense any of that gravitational force. It's there, but it's so small you're not going to feel it. Okay. Now, let's do example 2.18. I wish I could leave this on, but I really can't. So let's erase what's here. Let's see, can we go back? No. There. Let's use this. Gives me a little more room. What is the force of gravitational attraction between two 60 kilogram, that's 132 pounds by the way, students who are standing 1 meter apart? So the mass of student 1 is 60.0 kilograms. It's been decades since I was 132 pounds. I don't even remember it. Mass of student 2 is also 60.0 kilograms. Okay? The distance between them, the D here, is 1.00 meters. Not that far. You know, about from the tip of your finger to the opposite ear. Not that far apart. What's the force of gravitational attraction between them? Okay? Well, let's plug it in and see. The force due to gravitational attraction is G, and remember what G was? 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. Okay, that's the constant. Multiply that by the product of the two masses. Well, 60 times 60 is 3600 kilograms squared. Okay, 60 kilograms times 60 kilograms is 3,600 kilograms. Divided by 1 squared, which would be 1.00 meters squared. 1 squared is still 1. Okay? Unit-wise, the meter squares cancel out, the kilogram squared cancels out, and if any of you have a calculator that does scientific notation, do you know how to do that on a calculator? You do. Fantastic. If you don't, I'll try to walk you through it, but you see, different calculators manufactured by different companies have different keys, and you have to figure what those keys are. But if you have sort of a standard scientific calculator, usually it's 6.67, look for a key that's either EE or EXP. Look for a key that's either EE or EXP. Anyone find that? Okay. Press that, 6.67, and press that key. You'll see two smaller numbers, or spaces for two smaller numbers to show up. There you put in -11. Now, before you put in -11, don't use the subtraction negative. If you have a negative sign in parentheses, use that. If you don't have a negative sign in parentheses, look for a key that says plus minus. Or the oldest calculators used to have CHS, change sign. Any of you found either a negative sign in a parentheses, or a plus minus key, or a change sign key? What do you have? Oh, in parentheses? Okay, if you have it in parentheses, then once you do the 6.67 EE or EXP, then you can press that negative sign, but it's not the subtraction sign, and then press 1, and you'll see it pop up there. If you had the old plus minus key or change sign key on your calculator, you enter the 11 first and then do the change sign or plus minus. It's strange how they change over time. But once you get that number in, multiply it by 3,600, 3600, and you don't have to divide by 1, because anything divided by 1 is still the same thing. And what you're going to come up with is some number, and think what it is, something around 2.00 or 2 point something, 2 digits, times 10 to something like the -8. Is that what you get? 2 point something times 10 to the -8. No, I'm sorry. Wrong. 3 times 6. I was dividing, not multiplying. Okay. Yeah. Well, actually, I would be far off. 2 to 3 something or another, and that would still be times 10 to the -8 or so. What do you get? Anybody? What's that? Okay, what you got?
0, 0, 0, 0.
Wait. Oh, yeah, right, yeah, okay. You got all those zeros, okay? If you got it in the scientific notation, it would be 2.40 times 10 to the -7. Okay, I was off by 1 newtons, which was 0.0000. That's 4, 5, 6. Something like that newtons. If you're, most calculators don't have that many places on them, but if you have all those zeros, it should be 1, 2, 3, 4, 5, 6 zeros followed by 2 4s. Is that what you got? Okay. In scientific notation, you count the number of decimal places you're going. Since you're going to the left, that's going to be minus 1, 2, 3, 4, 5, 6. One more would be 7. 2.4 times 10 to the 7. -7 newtons. You gonna feel that? No. Okay. A newton is a very small force, and let's see, this would be 1,000th of a newton, 1,000,000th of a newton. This would be 24 billionths of a newton. No, you're not gonna feel that at all. Okay. Nowhere close. Okay. Okay. Now, let's do the other thing that they mention here. It's not one of the examples, but it's worth doing, I think. Okay? Let's take that Newton's gravitational law. That's F, this force due to gravity, is equal to G M times ME. That's your mass, or whatever mass you're trying to deal with. That's the first M. The second ME is the mass of the Earth, and this is divided by the D of the Earth squared. Now, I don't like D as much as I do R. So this is the radius of the Earth, okay? The radius of the Earth squared, okay? Well, what is the force due to gravity? That's mg, right? Mass times acceleration due to gravity is equal to capital G, which is this other thing, times m, that's the mass of the object, times the mass of the Earth over the radius of the Earth squared. Well, notice this mass and this mass cancel out, divide away. So they're no longer entering the picture. So the G here is 6.67 times 10 to the minus 11, okay? And that's kilogram. Okay, let's just leave it. Newton meter squared per kilogram squared. Okay? Later we'll go back and change that Newton. Multiplied by the mass of the Earth. Now, for those who have the big books, if you have the smaller book, I don't know if you've got this, but if you go to the front inside cover of your text, okay, you'll see there the Earth's radius and the Earth mass. So the Earth's mass is 5.97 times 10 to the 24 kilograms. 5.97, did I say? Yeah, 7 kilograms. That's the mass of the Earth divided by the radius of the Earth squared. The radius of the Earth is 6.38 times 10 to the 6th meters. But we're going to square that. Okay? So, here we go. Now, I'm also going to change my units. I started to before. A Newton is a kilogram meter per second squared. Okay? So, you got kilogram squared here. One of these is going to cancel out that kilogram, and the other is going to cancel out the kilogram up here. Okay? Here we have a meter squared down in the denominator. We haven't multiplied the numerator yet, but it's going to be a meter squared. That's going to cancel that meter squared out. Okay? And what we're going to be left with is meter per second squared, which is a good unit for G. So, to get the numbers, you got your calculator, 6.67 EE or EXP, okay, minus 11, so that should be on your display, multiply, I left off my units. This is 5.97 times 10 to the 24 kilograms. I left off my power unit. Okay, multiply this by 5.97 EE or EXP 24. Divide that by 6.38 EE or EXP to the 6th. Okay, back off from there if you can. Open a parentheses here. 6.38 EE or EXP 6. Close your parentheses, then square it. Okay? Your square key is probably an x squared or something like that. And then hit an equal and see what you get. Anyone do it so far? Again, 6.67 EEEHP negative 11 times 5.97 EE or EHP 24 divided by open parentheses 6.38 EE or EHP 6 close parentheses, hit the square key, and then hit the equal key.
9.78.
9.78. And if you rounded that to 2 digits, that would be 9.8 meters per second squared. That's where that comes from. The mass of the Earth, the radius of the Earth, and universal gravitational constant. That's exactly where we get our G, 9.8 meters per second squared. Okay. Now, I lost my place here. Let me see if I can get it back. Here we go. And all right. So I think we now have hit this slide. Now I believe we're ready to start talking about Earth satellites. Nope, not yet. There's another couple of examples. Oh! Example 2.19 was the one we just did. Okay, sorry about that. But there was a good graphic before you got to that, so we just did example 2.19 here. Okay. Right above this graphic in your text, there is one that tells how the force due to gravitational attraction decreases as inversely as the square of the distance from the Earth's center. So on the surface of the Earth, that is 9.8 meters per second squared is the value of G. Okay? If you go up another about 4,000 miles, which is 6,400 kilograms, which you'll notice, kilometers, that is about what you got here. 6.40, they rounded that, 6.40, 6,400 kilometers. The K kilo took care of 3 of these, 3 more digits over 6,400. That took care of the other 3. That's the radius of the Earth, okay? Which is about 4,000 miles, okay? If you go up another 4,000 miles, your acceleration due to gravity drops off to 2.4. It falls off to a quarter of what it was before. Quarter of this, okay? So if you weighed 154 pounds on the Earth, it's been a long time since I did, now you're down to 37 pounds, about a quarter of that, okay? Go up another 4,000 miles, 6,400 kilometers, and you dropped off by another factor of that's 230. Another, and you're down to an acceleration due to gravity of 1.1 meters per second squared, so you're down to 17 pounds. Go up another 4,000 miles, you're down to 9.5 pounds. Another 4,000 miles, 6.3 pounds. So this is what they call weightlessness. You're not ever weightless unless you're infinitely far from any large body. Okay? But anywhere out there in space, you're just so light compared to what you were on the Earth, it feels like you're weightless. Okay? So that's a pretty good graphic there. It's well worth a read. There is an example 2.20, so let's go back and do that one. Let me erase the ink on this slide. Okay? And let's do example 2.20. What would be the value of G if Earth were less dense with the same mass but double the radius? Okay, same mass but double the radius. So I wish I had left it up there. Okay. Same mass, so mass of the Earth was 5.97 times 10 to the 24 kilograms. 5.97 times 10 to the 24 kilograms. Okay? But double the radius. So the radius of the Earth, they call it D, I call it R. That is double this, and that would be 12.76. 12.76 times 10 to the 6 meters. Okay? Well, let's see what it would be then. G would be, remember from before, we had our universal gravitational constant, 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24th. I didn't put all my units in there, I probably should, but they'll come out, so we'll just leave them off for now. Divided by 12.76 times 10 to the 6, just so we're going to square. Okay? So we do the same calculation as before, but this time we double this before we square. So if you got, yes?
We're past 5:15, sorry.
Well, 5:15 is fine. We stop at 5:45. Yeah, because the lab is 5:45 to 7:45. If we had a test, we stop at 5:15. I'll allow you 2 hours for the lab. Yeah. Okay. The class started at 3:15 and it goes to 5:45. And the lab is 5:45 to 7:45. But when we have a test, then I'll do an extra half hour at the bottom, so I cut the lecture by half an hour. So yeah, thanks for telling me, but I need someone to keep up with that. Okay, so if you got your calculators, 6.67 EE or EXP, negative 11, times 5.97 EE or EXP 24, divided by, open parentheses, 12.76 EE or EXP 6, close parentheses, square that, and then press your equal sign. And what do you get as the acceleration due to gravity? If we had a bigger Earth but the same mass, double the radius, this will be the new Earth, okay? Basically what that does is cut it by 4, divide it by 4. 9.8 divided by 4 is approximately 2.4 meters per second squared. Okay? Much, much, much less acceleration due to gravity. Okay. All right. That being done, now we can move on to Earth satellites. Now, artificial satellites, what that means is stuff we send up there. The moon is our natural satellite, okay? We don't have many other natural satellites. Maybe there's some space stuff that's up there that floats around us, but the moon's our major satellite. We put a lot more junk out there. That must travel more than 320 kilometers above the Earth. Wow. If you look at the graphic we had before, 320 kilometers is not even close to, it's 1/20th of the Earth's radius up there. So it's not really all that far. But you got to be at least that far or else they're going to crash into the Earth. They must travel at least 8 kilometers per second to maintain the orbit to keep them from crashing into the Earth. And then they give this example of the GPS satellites. Like I said, those have to stay fixed above the same point of the Earth. So, and actually, who developed GPS? Does anyone know? Second? The military. Because they will keep track of ships at sea airplanes in the air, they wanted to be able to do. And then later, once they got that done pretty well, they said, you know, we can sell this or let this out into the public domain. Their equipment, I'm sure, is much more precise than what our GPS is. They claim they can do within a meter or two, whereas GPS probably gets you within 10 to 20 meters. So much more precise. Okay? So here we are in the middle of the Atlantic. Not in the middle, somewhere out there in the Atlantic. And you're wondering where you are. You need to be able to triangulate over 3 satellites. If you know how far you are from this one, your signal comes in from this one, you know you're somewhere on that subject. Well, you're not in Greenland, you're not in Canada or the U.S., so you know you're somewhere out here. This one tells you you're somewhere here. So that fixes you either here or here. You need a third satellite to give you precisely where you are that fixes you to be right there. Okay? And that's how our GPS works today. You have to have at least 3 satellites with it. Usually you have more than that, and that sort of refines and gets you more precise location. But that's what we do. If 2 of these satellites are too close to each other, then you have a lot more error. Try to get 3 satellites that are angularly as far apart as they can get. Okay? So that's what our GPS satellites do for us. Now, there is a blurb at the top of page 53, and it says gravity problems. It is a pretty interesting read. It's some of what I was just talking about before, how you're not really weightless in space. They call it weightlessness. You're not. You have some weight, but it's so much less than what you experience here on Earth, they feel like they're weightless. Okay? So that's worth a read to understand that. Then there's a pretty picture of Earth from space. Okay? And even though he lived way back in the 1700s, Newton described how you could put a satellite into space. That guy was awfully sharp. Didn't have the technology to do it, but he told you, if you ever get the technology, here's how you do it. And it worked. Okay. That's the only slide they have on Earth satellites. Okay? We have all sorts of satellites up there. The last slide in the chapter is on weightlessness. Okay? And again, this was referring to the blurb before. Astronauts appear to be weightless, but they're still affected by weight. Therefore, they're not technically weightless. They have very, very little weight, but they do have some. They actually are in constant free fall. If they were totally weightless, they would just be hanging out there and things would move on past them. But they're constantly in free fall, just like the satellites are in free fall. Okay? Guess who they had people behind the science? Isaac Newton. I said 1700s. He did a lot of his work in the 1600s, 1642 to 1727. Now, if any of you are keeping track of that, where were we as a nation at that time?
1727?
Yeah, he died in 1727. We weren't a nation, okay? In fact, I'm trying to remember if Georgia was even founded as a colony at that time.
I believe so.
Huh?
I believe so.
Yeah, I can't remember. They were founded in the 1700s, okay? They had not been a colony very long at the time of the Revolution. Now, Massachusetts, Virginia, they had been colonies for quite a long time. They were like founded actually before he was born.
Georgia was founded in 1732.
I was thinking 35, but yeah. So actually he was dead before Georgia was founded. Okay? He died in 1727. So, but Massachusetts and Virginia, I think Virginia was 1608 or something like that. So that was before he was born. Massachusetts was about the time that he was born, or maybe a little before. and the other colonies were along in there somewhere. Okay, Georgia hadn't been founded yet. So that was how long ago it was. Okay, incredible, incredible mind. You can probably find several potential paper topics here. You see several other names mentioned, like Albert Einstein, Archimedes, incredible person here. Remember, this cannot be your source for your paper. You have to get something outside the book for your sources. This can give you ideas, but you need to go outside the book to get your sources. Okay. And it doesn't even begin to say everything that he did, but he was incredible, how much brand new stuff he came up with, and it still holds today. There is a concept applied apparent weightlessness. Do y'all know how the astronauts train for weightlessness?
Don't they have that special plane?
Yes.
It's like zero gravity.
You know what their nickname for it is? The vomit comet.
Yeah.
Okay, because what they do, they basically go almost in the free fall. They go as high as they can get up there, and they go in the free fall, so they're floating around for only a few seconds. But then to come out of it, then they have to come out of it real suddenly, and boy, the G's that you pull, it's incredible.
My physics teacher in high school got to do that.
What's that?
My physics teacher in high school, he got to go on that.
Oh, he did? What did he feel about it? Did he
He said it
throw
was
up?
long.
Oh,
He didn't have a problem with it.
Okay.
He said it's a lot longer. It feels a lot longer than it actually is.
Yeah.
Yeah, it's just quite a few seconds. But
Right.
He
Yeah.
said it feels like, because it's so new,
Yeah,
it felt like
exactly.
it lasted a long time.
Yeah. And where did you go to high school?
Florida.
Oh, Florida. Okay.
Yeah.
Yeah, no wonder. They close enough to go out. Okay. We finished the chapter. That means it was a long chapter, wasn't it? We'll do our last lab today on chapter 2. We will have the test now on chapter 2 on Thursday, the last 30 minutes. We'll get started a little bit probably in chapter 3 just to not waste your tuition dollars here. I say this every chapter, and I'll say it again. I will say it every time. Nothing replaces reading the chapter. As you notice, several whole sections in this chapter were covered with one slide with just a few words and a picture. You can't get everything out of a few words and a picture. So please read the chapters, okay? Once you finish reading the chapter, this has a fairly long summary, which hits the high points. But without the context of the chapter, the summary may not make a lot of sense to you. This chapter has a huge number of summary of equations. 12 equations. The last chapter, 1. Okay? So a lot more equations here. Key terms, this is about normal here, maybe a little on the short side. But they list these alphabetically, but they put the page numbers where it was first defined or referenced. So you can do that. Applying the concepts. This is about normal. 47 questions here, multiple choice. That, to me, is the best thing to study for your test. You will not see the same questions, but you'll see the same material questioned about. Okay. That's on pages 57, 58, and 59. Okay? They have all the answers there. If I would say go through and you guess the answers, look at that, see how many you get right, figure out why you missed the ones you got wrong. If you can't figure it out, be sure to ask me in class the next time. Then they have questions for thought, fewer than normal, 12. Good to think through those. For further analysis, maybe a couple more than normal, 6. There's a little invitation to an inquiry about the domino effect, so you can read that if you want to. The parallel exercises for those who have the big books or the newest of the thin books. If you have the older thin book, it won't have them. Parallel exercises, the Group A exercises have their answers in the back, and they have 31 questions here. That's quite a few. I would take a look at least a few of those, one of each type. because those are, and their answers are in the back, okay, in Appendix E. Good deal. Yes, sir. Anytime you're ready for it. Okay. Good deal. Thanks. Goodness, I got a lot of grading to do. Okay. All right. More. Okay. All right. That's it. Any questions on Chapter 2? A pretty hefty chapter. And Chapter 3's not far behind. Okay? So let's get out of Chapter 2. And we have about 10 minutes. So let's at least get started in Chapter 3. And just, you can't see this. I don't know why the projector won't do it. But Chapter 2 had 5,471 kilobytes in its slideshow. Chapter 3, though, is considerably less, just around 3,000. Just less than 3,000. Actually, Chapter 1 had more than Chapter 3, but Chapter 3 is a longer chapter. So let's hit Chapter 3. Again, you can't see it, PowerPoint. All right, there we go. So let's go from current slide so you can see it. Okay, Chapter 3 is talking about energy. This summer, in between summer term and fall term, we had close to a week off, and my wife just happened to have a professional meeting in near Salt Lake City, Utah. And since I was off then, I got to go with her. And we drove through some of the areas out there, and we saw some wind farms, not quite this dense, but very, very similar to this. I mean, wide open spaces there, lots of wind there, and they had these wind turbines out there just spinning away, okay? Great use of energy. Now that's illustrating several things about energy. There's several kinds of energy. You've got the kinetic energy of the wind, and it's turning the turbines. The turbines are then turning a magneto, I guess you would call it, which is producing electricity. A generator is what it is. And then, so you change kinetic energy of the wind, mechanical energy of the motor, to electrical energy that then we can use. And then the electrical energy can be used for light, for heat, for motion, for just about anything. Your calculators, your telephones, whatever. The core concept in this chapter, which is on page 62, energy is transformed through working or heating, and the total amount remains constant. Now, we already mentioned, by and large, mass is considered to be constant. The total mass does not change. Linear momentum is considered to be constant. That does not change. We didn't talk about angular momentum. We'll mention that slightly in lab today. It does not change, okay? And total energy doesn't change. But as I just indicated on that last slide, energy changes form so smoothly and effortlessly, it's hard to keep up with where the energy is, okay? Here's a picture of a dam. This is the Glen Canyon Dam on the Colorado River between Utah and Arizona. I guess this is the last dam up before you get to the Grand Canyon, because Grand Canyon is in Arizona. So it's backing up water behind the dam, and that's giving what we call gravitational potential energy to that water. The water falls. The turbines are down here at the bottom. The water falling picks up speed. That gives it kinetic energy. Turning the turbines, that gives it mechanical energy. And the turbines then produce electrical energy, which is then transmitted throughout the Southwest. Okay? But the total energy remains constant. It changes forms so many different times, it's hard to keep up with it, but the total energy is constant. Okay? So, the fundamental law here is the conservation of energy. Now, this is in your text, basically in the overview, I think. It's not really following the slides too well here. Yes?
Is petroleum a kind of gas?
It's what?
Is petroleum a kind of gas? Because gas gives energy sometimes.
Okay. I didn't mention that one. That is, like we saw behind, the water behind the dam was stored mechanical energy, potential energy. In petroleum, it starts with these little green leaves out here. Okay? Those little green leaves have this material called chlorophyll. What does chlorophyll do?
It cleans.
Okay, now that's Clorox. Okay. Okay, what does chlorophyll do? It's what?
Absorbs light.
Okay, yes. It takes energy from the light, which is electromagnetic energy, radiant energy, and converts that to chemical energy. Because it takes that electromagnetic energy from the light, and through chemical processes, there's a couple of chemicals, ADP and ATP, adenosine diphosphate and adenosine triphosphate. They exchange energy and store energy, and that's what then the carbon dioxide from the air, the water from the earth, that combines with these energy things to form chemical bonds which form our simple sugars: glucose, sucrose, fructose, and all the other toses that you have there. Those are chemical energy. Well, that chemical energy then, when the leaves fall, go into the soil, into bogs, into peat, things like this, in time they, under great pressure and a lot of time, high temperatures, they change to petroleum, or coal, or natural gas, and all those are stored chemical energy, stored in the bonds between those, and then when we burn them or oxidize them, that's when that energy is released. So it's radiant energy from the sun that was stored millennia ago, okay? That's what we're burning when we burn our fossil fuels. At an enormous rate. We have probably burned many millennia worth of things. How many more do we have? Okay? That's the issue. Okay? So, manifestations of this conservation of energy, you just hit on it. You can have energy of work, the energy of motion, the energy of position, the energy of radiation, that's light, or other types of radiation, heat, chemical energy, that's what, yes.
How does energy of position work?
Okay, that was the storing the water backing up behind the dam, that's positional energy. Then when it's allowed to fall, that changes to kinetic energy, okay, energy of motion. But, okay, I'm doing work on the book right now. I'm lifting the book. I'm doing work, it's getting more and more energy because of the work I'm putting into it. Huh? It is, okay? Now, if I were to, I'm going to use Yursi's foot here. If I were to drop it from here, it might hurt a little bit, okay? But if I were to drop it from up here, it's going to hurt a lot worse, okay? Okay? You want me to demonstrate? Okay. Oh, no. The reason for that is I've added more energy to it. That's energy of position. The higher it is, the more energy it has. So the further it drops, the more energy it exerts on its foot. Okay. All right. You also have nuclear energy, energy in the nucleus of an atom. Mass itself is a form of energy. Okay? I guess we're going to have to stop there since we are out of time. I wish I could find exactly where this is in the text. Let's see, do they say which slide this is? Slide 3, okay. I'm just going to make a note that we're going to start on slide 3. Okay. Okay. What's that? Okay, we're going to have lab right now. Is she leaving? Huh?
She's not leaving.
Oh, okay, good. Okay. So let me go on and mark the roll again because it's 5:45. Rachel's still here. John's still here. Chris Davis is still here. Yale is still here. Thomas is still here. Okay, Hunter is still here. Sean never made it in today. Okay. Justin's still here. Eric is still here. Ashley's still here. Andrew's still here. Chris Lynn hasn't made it back yet. David is still here, or is he? Did we lose David at break? No, David came in. Did he leave? Okay, so we don't have David. Chelsea just got here. Okay. Alex is still here. Yurosei's still here. Melba's still here. Samuel's still here. Angel's still here. Lisa's still here. Scotty didn't make it in at all today. Adam's still here. Ashley's still here. Kevin's still here. And Garrett's still here. Somewhere back there. There he is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 21. 3, 6, 9, 12, 15, 18. All right. Let me pass out the lab before we lose anybody. Okay? Or let me just pass out. Okay. All right.
No, I don't.
You said 259, right, Mr. Bell?
What's that?
You said 259?
That's where we're going. Let me give you the labs first. Don't go in the room until we're sure nobody's in there. Okay? So pass 2 over. Pass 2 over.
Hey, that's nice and light. Look at that, guys. You guys can take that in no time.
Okay, we hope.
You say that, Hey, Adam, you get your Mountain Dew can?
Yeah, Adam, how much do you get? It says it's 2 labs, it's 1 lab. Yeah, we're going down to the lab and do it. Thank you. Okay. And you still got the take-home test.
Still got to take it.
Yeah.
I want to talk to you about it, but I think I lost it.
Okay. I don't have it with me, but we can get it. Maybe while y'all are doing the lab. We'll see. Okay, I'm going to end the slideshow.
Yeah, I got laryngitis. But my voice is all,
Okay. And I'm going to pause. Let me get a copy of the lab. All right. We got 7 stations, 4 over here, 3 over there. 3 people per station, and everyone needs to do this, okay? It's real simple. What you do, we have a mass, and you'll look at it, and you see on one side it says the 100-gram mass sitting on a piece of paper here. What you're to do is pull horizontally. Don't pull up. That's going to mess things up. Pull just horizontally in a very quick pull, okay? And describe what happens to the mass. That's first page, Roman numeral 1, letter A, number 1. Quick jerk, pull the paper, what happens to the mass. Describe it however you see it happening, okay? If you tend not to get what you think you're expected to, I'll watch you do it and see if you're doing something wrong. So 3 people to each of these stations here. Go up, each person do it, record what you see. Did all of you notice? What did you find the mass doing?
It stayed in one place.
Stayed in place.
Or moved a little bit.
Or moved just a little. There's a little bit of friction between the bottom of the thing and the thing, and the bottom of the mass and the paper. Number 2, what property of matter did that action demonstrate?
Position?
Second?
Inertia.
Inertia. It stayed in place. Inertia. Okay?
I'm just that good.
Now, everybody's seen that and are convinced of it, right?
Yes, I do not believe that.
All right. All right, this is unfortunate now. We got so many people in such a small room. With everybody, if you finish with this part, we move to the second part on B to be worked as a whole group. So everybody has to cram into this room. Now I'm going to have to talk really loudly because my computer's over there and I'm over here. And try not to damage anything. That's a very expensive piece of equipment there. So yeah. Everybody get in here. Okay. Yeah. Okay. This is not expensive, but it takes a long time to set up. Okay. Okay. But this is expensive stuff. Don't damage anything. But everybody get in here somewhere. Huddle up, team. Okay. Okay.
Random question real quick. Is this one of those,
Van de Graaff machines try to stop. It doesn't work.
Okay.
They just, all right. Is everybody in?
I believe.
Is there anybody else out there?
No, one person.
One person. Okay. Okay. We got more room in here. It'll be helpful to come in and see. So you might not be able to see from where you are. So we got plenty of room. Okay. But I do need 2 volunteers.
You got one right there. What are we doing?
Okay. Just need 2 volunteers.
Thomas,
No.
contribute.
Well, you may not be strong enough, but we'll see. No, come on.
I am not
Okay.
positive.
Okay. You said first, right?
What's up, Thomas?
So you get to choose your device. You want the one over here or the one over there? Okay. So stand up. Okay. And what you're to do, no, don't touch that one. What you're to do is take this thread here, wrap it around your finger. Okay. Now this is B. One person in the class is exert a steady pull. So start pulling downward and pull and just slightly increase the pull. Keep increasing the pull until one of the threads breaks. One of the threads breaks. So wrap it around your finger. Just pull down, pull down. Oh, which one broke first? The top one. So everybody records that. Okay?
You'll be okay.
Top thread broke first. Okay?
You okay, Andrew?
Everybody saw it too, right?
Yes, sir.
Well, you need to be close enough to see. Okay. Top thread broke first. Okay. So you come over here, and very similar to him, you wrap your finger around that. But this time, don't pull at all. Give it a lot of slack, and then when I say so, or when you choose to, go a real quick jerk downward. Okay, I'll hold that. Anything for you. Okay.
Can you stand behind the contraption?
Okay. Slack,
Oh,
slack,
boy.
slack.
Other way.
Anytime,
Oh,
pull
boy.
straight down. Very suddenly. Oh, which string broke then?
The bottom one.
Bottom one. You get your stuff.
The recording
Thank you, I appreciate
information.
it.
All right, glad to. Well done. What's that?
That's what I'm saying.
Okay. Now, everybody, hopefully all of you saw that, using Newton's laws of motion, at least two of the three, explain the differences in the two outcomes. Why did this one, the top string break, thread break, while on this one, the bottom one broke?
He did it a lot slower.
Say again?
He did it a lot slower.
Okay, and what difference does that make?
A big one. It's allowing it to put
That's
more
acceleration.
force into the top thread.
Ah, you're getting very close there. Notice over here, he was pulling downward on the thread, the bottom thread, and because he was pulling slowly, that also was pulling, but the top thread had more force on it. It had the weight of the thing, which is force, plus his pull, so the top thread had more net force on it, the bottom thread only had his pull. So there was more net force on the top thread. And which of Newton's laws deals with net forces? Second law, exactly. Okay? So, the first device, the top thread broke first because there was more net force on the top thread. Second law. Make sense?
Yeah.
Yep.
How in the world do you describe what happened over here? What did Hunter do wrong? No, I mean,
Everything.
What was the difference here?
There's a very quick movement, causing the bottom string to break.
Why?
It moved quickly.
Okay.
FM.
Say again?
FM. It's an abbreviation.
Put more net force in it.
What's that?
You put more force into the bottom string than what the top string had on it.
Why?
You
Okay.
exerted the force quicker.
Say again?
You exerted the
Force more quickly. Okay. That's similar to what we did out there, wasn't it?
But this, I know that probably doesn't matter. Was the strings the same thing? Or whatever?
Well, they were about the same length. But the deal was,
One was from the bottom.
what's that?
That one did not go all the way through to the bottom.
What do you mean did go all the way to the bottom?
Where did he pull the string from?
He started real slack and then pulled straight down. He was pulling down, but very slowly. Think of the, okay, this has nothing to do with a Hunter here. Think of the quick jerk out there. Never mind. Okay. Okay. What was that? Out there? Inertia. The inertia of the mass, it was just sitting here, a very quick pull. The inertia of the mass,
Didn't change.
this string hardly felt anything because the inertia of the mass held it in place. And which of Newton's three laws is the law of inertia?
First.
The first.
First.
Okay, very good. So you need to explain both of them. So number 3 has two parts to it. And actually, yeah, a little bit of a description and two parts. Okay. Now, while y'all are finishing writing up, I'm going to go set up the second part out here. If you wouldn't mind actually bringing the scale and the writing on it. And
What is it, the inertia of the mass?
oh, I hope not. Okay.
I'm out of this last.
And it was
What we're going to do now, and again, we're going to work it a whole slab here, because we don't have enough apparatus to do it. So I'm going to do the stuff that you're going to observe and explain what's next. I do need 4 volunteers that have volunteered before, and each one of you needs to either zero the scale and place one piece small on the scale. If you can't get it to stay on there, then put the rope, the weight in on the scale, then zero with that, and determine the mass of the 4 balls. 4 people, any 4, will come up and determine the mass of those 4 balls. Determine the mass of the 6 balls. Okay, 69 grams, but don't record it in grams. Record it in kilograms. How many kilograms is 69 grams? 0.69 kilograms. So record the mass, 0.69 kilograms. Oh, that's right. Thank you. Say again?
In grams?
Okay, you read it in grams, so record it in kilograms. 0.069 kilograms. Okay? I'll take that ball and use one of the others.
You're not a pirate. These 35 inch tall slits, man, you're almost down.
Say again?
0.030.
0.030 kilograms, that's the small ball. Okay? Somebody else come measure one of the other large balls.
What? 0.030.
0.030. Huh?
30 grams is 0.30.
No, that would be
So it would be
30. That would be hectograms, which we don't use. It's move the decimal 3 places. If it's 30, move it 3 places, 0.030. Okay, so I want to measure one of the other 2 large balls? Come on. I've got all night. I'll be here till 6. I mean till 8.
Which one's the been measured?
Okay, did you zero it first?
The plate was on there, it should have already good.
Well, but the thing is, if you're going to be measuring, you need the zero so you'll know where you're looking. $71 grams, which is how many kilograms? 0.0. Hand it to me. Okay, good deal. Thanks. And somebody else come measure the last. Now somebody else come measure the last. No, you need. Need somebody else to come. Yeah.
0.71.
Zero the scale. So if you're looking at the scale, I want you to look at it the same way when you're zeroing as you do when you're measuring. Otherwise, you don't know where the other person was looking. It's up to you. Okay. Put it in. And look at it the same way you did that one. And you zeroed it. What do you get?
68.
Figure?
68.
68 grams. So how many kilograms was that?
0.68.
What? Say again?
0.68.
Nick?
0.68.
0.68. Move the decimal 3 places.
So 0.071 was the other one?
Yes.
Alright.
All of them have a .0 in front. Right?
Yes.
Okay. Now, we're through with the scales for now. What I'm going to do, what's that?
I didn't have to.
Okay. You might get from someone what those measurements were. Okay. I put one large ball stationary on the track. I'm going to roll another. The 3 large balls are basically very, very close to the same masses, right? Okay. So I'm going to place one on the track, and I'm going to roll another one toward it at approximately 1 meter per second. Well, I can't know exactly what it is, but whatever I'm going to roll it at, we'll assume that's a meter per second. Okay? What I want you to do is pay attention to what happens to the 2 balls right at the time of collision. Now, the reason I say right at the time of collision, something else will pick up later, and that's because we have 2 forms of momentum going on here. The ball moving down the track, that's linear momentum. But the fact that it's going to be rolling, that introduces, did you get a laugh? Okay. All right. The fact that it's rolling, the ball will have a little bit of angular momentum. Okay? Now we're trying to minimize that. That's why I'm going to try to roll it really quickly. I'm going to try to slide the ball down there so it's not rolling. It's going to roll some. Okay? So therefore, I want you to pay attention to what happens immediately after the collision, not what happens a little bit later. You'll see what I mean, I think. Okay? So y'all are watching?
Yeah.
I'll try to get out of your way, but everybody can see what's happening here. If you can't, stand up so you can see.
Got it.
Okay?
Yeah.
I'm going to try to go, and I might need a catcher over here.
You're saying that's all you.
Okay? Okay, yeah, you don't have to get super close. Yeah, but that's fine. You can be there. Okay, you ready? What did you describe happened right at the point of contact?
It stopped. The very first one stopped.
The first one stopped, and the second one picked up. Now, would you say it traveled about the same speed as the first one coming in?
Yes.
Okay. So,
Those are set up as good deals.
okay. Now, so you described, you named whichever ball was 1 and whichever was 2. You know which one's originally stationary, which one's final. But you did notice this, the ball I rolled stopped, but then it started rolling a little bit because of angular momentum. We're interested just in the linear momentum. So, if I was indeed rolling that at a meter per second, what was the initial momentum of ball 1? Whichever one you named 1.
Meter per second.
Huh?
Initial? Meter per second.
That's a unit. I need a number. Huh?
1 meter per
Okay. A meter per second measures what?
Speed.
Yes, speed or velocity.
So what do you want?
Okay. I wanted the momentum. That's why I said what was the initial momentum?
You gotta know how many meters. Which is measured as what?
Which that's my question to you. What's that? Mass times velocity. What's mass measured in?
Grams.
Or kilograms. And velocity in?
Meter per second.
Okay. So what was your initial velocity, initial momentum of ball 1? Now which one did you count as ball 1?
The moving one.
The moving one? So what was its initial momentum? You got its mass. Pick one of those big ones up there. And then
1 meter per second. Grant.
1 meter per second is a speed, a velocity. That's not a momentum.
How do you find
Multiply by the mass. And what would say?
what's going to be the unit?
Okay, what would be the
So
unit?
which weight do you want us to use?
Which what?
Which weight do you want us to use?
None on the way.
Kilogram per meter second squared?
Which mass do you use? That was the right question. Okay. Okay. It was one of the large balls. I don't care which of the large balls you use the mass for. They're so close. Yeah.
0.069 kilograms per meter.
Kilogram meter per second. Okay. 0.069 he chose. Kilogram meter per second. That's the unit for momentum. Kilogram meter per second. Okay.
How do you write that? Kilograms and then just
kg, and then you can either put a dash or a dot, meter, then a slash, second. Kilogram meter per second. Yeah. Okay. Let me. I should have it. Okay. That would be. Good. Someone found the trash can? Okay, I got it. Here we go. 0.069 kilogram meter per second. And you can put a dot or a dash in between those if you want to. Is that what you're asking?
I think that's
How hard? Yeah. Is that answer enough?
Yes, sir.
Okay. All right. That was the initial momentum of ball 1. What was the initial momentum of ball 2?
0.
0, because its velocity was 0. Okay?
You gotta have a unit for 0?
No, you don't. Okay? You can if you want to, but yeah.
What kind of study do they use?
What?
What kind of study did they use this in?
Okay. We talked about collisions. They use momentum in collisions. They use them in, various things like, when they're figuring out trajectories, when they're figuring out things like projectiles. Use it all the time. Anything
So
that
when you're shooting something, or when you're hitting something else.
Yeah. But in automotive design, you want your bumpers or your various components of the car to be able to withstand given momentum. Okay. So, what was the initial momentum of the system then? What was the initial momentum of the system? The two balls together.
Would that be the average of the two?
The half?
No. Some.
Oh.
Some, so it'd still be 0.069.
Exactly, because the other one was 0. Okay? Now, I didn't have room to put this question down. What appeared to be the final momentum of the system? The first ball stopped, but the second one took off at about the same speed the first one did. So, it had the same final momentum. There's no place for that. I'm just asking. Does it appear that momentum was conserved?
Yes.
Yes. Okay, very good. Now this time I'm going to put 2 large balls on the track, and I need to have them keep touching each other. And for some reason they tend to separate. So I thought I had them. Okay. Now I'm going to take another large ball. I'm going to roll this toward those 2 balls, and what would be your prediction of what's going to happen. Yes.
The momentum's going to travel through the ball.
Yeah.
You travel through
the ball in the center and carry on to the ball on the outside.
Okay, so what will be the final result?
All three moves.
Ball 3 moves,
Yeah. Ball 2 stays
ball 2 stays stationary,
Ball
ball 1 stops. That's what the projection is. Now, would momentum still be conserved if these two took off at half the speed of the first one?
No.
Yeah, it would. Momentum will be conserved, but later we'll study kinetic energy and it wouldn't be conserved. So let's do this with momentum. We have a prediction there. Can everybody see? I need a catcher. On the right.
They can stay,
Okay.
like you said.
Pretty much just what he said. Okay? The first ball stopped, the second ball didn't move, and the third ball took off with about the same speed of the first ball coming in, right? Did it appear? Yes.
Oh, no, I was just gonna, never mind.
Okay, did it appear that momentum was conserved there?
Yes.
Yes. The first ball had all the momentum, these had none. The third ball had all the momentum, the first two had none. So yeah, it looks like momentum was conserved. Okay. This time I'm going to, with two large balls, roll them toward each other. Okay? And I'm going to try, and I'll probably need catchers on both sides here. Okay? I'm going to try to roll them at the same speed toward each other. What will be the initial momentum of ball 1 then?
0.
I'm rolling it toward the other.
0.69 kilograms.
0.069 kilogram meter per second. If this is positive, this one. What would be the initial momentum of ball 2? Second. But momentum is also a vector quantity. That means a vector. Okay. Okay, vector quantity. So it will be the opposite. That would be negative 0.069 or something close to it, kilogram meter per second, because it's going in the opposite direction. So what would be the initial momentum of this system?
0.
0. Okay, even though both balls are moving. Okay, because they're vector quantities. I didn't mention that in class. I wish I had. Momentum is a vector quantity. Okay. Now, what do you expect to be the result once they collide? They both bounce back opposite direction. That's the idea. If they both stayed in the center, that would be conserved momentum, right? But kinetic energy wouldn't be conserved. But we'll talk about that later. So let's see if your prediction holds. Ready? All right. Final momentum of this ball?
0.69 kilograms.
But in the negative direction. It was positive, now it's negative. Final momentum of this ball? Positive, 0.069. So sure enough, it does look like momentum was still conserved. Yeah, one's negative, the other's positive. Well, you don't have to write it down. This is just for thing. Well, yeah, you can write it if you want to. That's fine. You describe the motion however you want to. If you want to use those signs, you can. So momentum stayed 0 throughout this whole event. Amazing. They never stopped moving, but instantaneously they were still 0. Okay. Now I'm going to place a large ball near the middle of the track and roll the small ball toward the large ball. Okay? I want your prediction of what's going to happen here. Okay. We just did G and we're getting ready to do H. Yes. Okay.
Small ball towards the large ball.
Second.
I was just saying, he's rolling the small ball towards the
I'm rolling the small ball toward the large ball. And what? No. Okay. Rolling small ball toward a stationary large ball. Yes.
Just the large ball is going to move, but a lot slower.
It's going to move.
Okay. How about the small
The
ball?
small ball is going to bounce back.
Okay. Here's our prediction. Huh?
It's going to move at half the speed because the small ball weighs half at the big ball.
Okay. It's not quite, but it's
Close.
well, the point. What was it, 069 and .030? Yeah. It's close, but not quite. Okay. So let's see if that indeed happens. Everybody ready to watch?
Sure.
Okay. Can you see over me?
No.
Yeah.
Okay.
There you go.
And what did you notice? Exactly what was predicted, right?
Ball moved back a little after it hit the big ball.
Yes, after it was hit by the big ball, it did recoil, and the small ball and the large ball took off, but at a slower speed in this way. Now let's think about the momentum. All the momentum initially was in the small ball, right? And it wasn't that much momentum because it's, again, like Hunter was saying, a little bit less than half the mass of the large balls which have been rolling before, but at the same velocity. So that's a very small, fairly, about half the momentum before. This one takes off this way, and actually this has more momentum coming this way than the small ball had coming this way. Can you believe that?
Because it bounced back.
Because this one bounced back and that had a negative momentum. The total momentum had to be the same, so this one actually gained more momentum than, it gained the same amount the small ball lost, but the small ball's loss was stopping and going in the opposite direction. So this had more momentum coming this way than that one. Okay. So now I'm going to place the small ball on the track, stationary, and roll a large ball toward it. What do you think is going to happen here?
The small ball's going to increase. Or no, the large ball's going to follow the small ball.
Okay, follow it at the same speed or a different speed? It's going to reduce its speed. The small ball is going to go at a larger speed. Now, especially right at collision. After a while, the large ball may catch up, but that's because of angular momentum, not linear momentum. So let's see if that indeed happens. Okay, you ready? And sure enough, small ball took off and went first. And my catcher in the rye, no, I got it. Thank you. Okay. Okay, one more. It's not on the page. You can write it on the bottom, or you can flip it over and write it on the back, or wherever you want to write it. You can write it on the back of the previous page. I don't care where you write it. One more. And this one I'm going to, remember number F up there rolled one ball toward two stationary. This time I'm going to try to roll two moving toward one stationary. And I want a prediction.
They're all going to stop.
All going to stop?
The one in the back is going to stop. The two on the farther side are going to keep going.
Okay, that's what my prediction is
If you
here.
can
We
roll
have-
at the same time, like exactly the same time, it's probably stop.
What's that?
If you can roll it exactly at the same time, it's probably stop. Oh wait, okay, I thought you meant from each side.
No.
Okay, I got you.
Okay. All right, need a catcher in the right.
Got it.
Okay. And these are hard to roll this way, so it may not come out exactly. Yep. Two ball took off. This one should have stopped, but it had some angular momentum, so it kept rolling. Okay. So write that down either at the bottom margin, on the back of either two sheets, wherever you want to write it. You didn't see it? Okay, we can do it again. Okay, rolling two large toward one large. Can you see?
So the back one stopped, and the other two in front of it
kept rolling. So in other words, the third ball took off, the second ball never stopped, and the first ball did stop. Okay? However you want to say that. You decide if I can read it and understand it. You get credit. Okay? Was this worthwhile?
Yeah.
Illustrate momentum and Newton's laws. Okay? And it was way too short, wasn't it?
Oh, it was perfect.
It was the perfect amount of teaching.
Okay.
It was great.
So, okay, if you need to get data from someone, you certainly can. And there's a Chris, the first part of it is up here. You can do it yourself if you want to. You know, but the second part you can't because it destroyed the effort. I'd have to retire the thing to just finish. Okay, now just a little bit of a reminder. We were going to start Thursday on Chapter 3 where we left off today. We didn't get very far today. So we'll take off and go. We'll go for about 2 hours. The first lab for Chapter 3 we'll be able to do in the next 2 hours, and then the last half hour will be the test from Chapter 2. Got it? So if you want a formula and equation sheet, please bring it. Yes. It's approximately 20. Okay? More like last chapter.
Hey, last lab, it says something about 12 questions.
Second?
On the top of the lab, it says something about 12 questions in the book.
No. Don't worry about that. That was, I used to require that. I don't know why I don't do that anymore. Shouldn't we do that? Don't you think?
I'm learning up. I got it all.
Hunter's wanting me to start asking questions, right? Answer your questions. All right, you want to go get the test? Yeah, I got the okay. Well, we're grading from guys from home.
Now they're again.
It should be, but.
Yeah.
I got a
Anyone who wants to turn something in, you can place them right here. I'm going to go get a test from the lab. That was with each test from now on, going to be a lot more like the last where, 2 pages, about 20 questions. It won't be $20. Yeah, but that's fine.
One for you.
I think I got it. First one's gonna be down, and the second one ain't gonna be. What is this? Yeah. You're gonna do third lab.
You got it back. You got it back.
I forgot that you came in late, so I didn't use my car. But, yeah.
Thank you.